When you really get down to it, what is the universe made of? Well, it's particles, right? Electrons, photons, quarks, the tiny building blocks of everything. And for the longest time, we thought we had the basic rules of the game figured out. It seemed like every particle out there fell into one of two very, very different families.
So, on one hand, you've got the fermions. You can think of them as the anti-social particles of the universe. They're the stuff matter is made of, electrons, protons, and they have one very strict rule. No two fermions can ever be in the exact same quantum state. On the other hand, you've got the bosons. These guys are the social butterflies, the particles that carry forces, like photons. They absolutely love to pile into the same state, which is exactly why something like a laser beam can even exist. So, for decades, physics seemed pretty simple. You were either a fermion or you were a boson.
But what if that whole story, that neat and tidy two-party system, wasn't the whole story? What if there was this secret third kingdom of particles hiding just out of sight? Okay, so to figure out where this hidden kingdom could be, we've got to first understand why we were so sure there were only two types of particles to begin with. And the reason, believe it or not, comes down to the dimensions we live in. See, here in our cozy three-dimensional world, every single particle has this built-in property called spin. It's kind of like its fundamental orientation in the universe. And the math that describes our 3D space is incredibly strict, like zero wiggle room. It says that a particle's spin has to be either a whole number, which makes it a boson, or a half number, which makes it a fermion. That's it. No other options allowed. It was a fundamental law of our universe, or so we thought. But here's the kicker. That rule only works in our universe, in our three dimensions. So, what happens if we start playing with the rules of the universe itself? What if we just take away a dimension? What happens when we step into a world that's totally flat, a two-dimensional plane? Well, the second you do that, the moment you step into this theoretical flatland, all those strict mathematical rules that kept everything so neat and tidy in our 3D world, they just kind of fall apart. All of a sudden, that clean line between fermions and bosons gets blurry, and a brand new possibility pops into existence. And this is where our new particle is born. Say hello to the anion. The name really says it all. It can have any old fractional spin it wants, and it follows any kind of weird statistical rule you can imagine, putting it somewhere on a sliding scale between a fermion and a boson. But why? Why does just losing one dimension unlock this totally mind-blowing new physics? Well, the answer is really, really cool. It's not just about the particles themselves. It's about the paths they leave behind when they move around and interact. It's all about how the universe's memory works in different dimensions. Okay, think about it like this. Imagine the path two particles take when they swap places is like a piece of string. Now in 3D, that string has a whole lot of room to move around. But in 2D, it gets stuck. This one simple idea is the key to, well, everything. All right, so let's look at 3D first. If you take two identical particles and swap their positions and then swap them right back, the universe fundamentally has no idea you did anything. It's exactly like taking a string, looping it around a ball, and then you just lift it off. Poof! The loop is gone without a trace. The history is completely erased. The takeaway is that doing two swaps is exactly the same as doing nothing at all. And that mathematical reality only leaves room for two outcomes, the one for bosons and the one for fermions. But in two dimensions, oh boy, everything changes. Swapping two particles in a flat plane is like looping a string around a pole that's permanently stuck to a table. Now, if you swap them back, you're just looping the string around again. You can't just lift the string off the table, it's trapped. The path, the history of those swaps is now a permanent braid in spacetime. The system remembers every single swap. The history is not erased, and that means two swaps is absolutely not the same as doing nothing. And that is the whole ballgame right there. In 3D, particle exchanges are just simple swaps, permutations you can always undo. But in 2D, they form what's called a braid group. The history of the swaps creates a real physical record, a kind of topological knot that opens up a whole spectrum of new possibilities. This is the mathematical loophole in reality that gives birth to anions. Okay, so this is all super cool theory, right? But it begs a massive question. Does any of this actually matter in our real three-dimensional world? Do these weird 2D particles actually exist anywhere? And the answer, incredibly, is yes. So while you're not going to find an anion just floating around freely in 3D space,
They can and they do show up as what we call quasi-particles. Think of them as collective behaviors, or excitations, inside materials where electrons are forced to live in a totally flat two-dimensional layer. So they're not just some mathematical curiosity, they are absolutely essential to explaining real-world physics.
The absolute smoking gun for anyons is something called the fractional quantum Hall effect. Back in the 80s, physicists found something bizarre. When you take a super thin sheet of electrons, trap them in 2D, cool them down to near absolute zero, and blast them with a huge magnetic field, their electrical conductivity did something that should have been impossible. It would lock into place at these weird, precise fractions. It was a total mystery. Our standard physics, which just saw electrons as fermions, had zero explanation for it.
The big breakthrough came when scientists realized they were looking at the wrong thing. The answer wasn't in the individual electrons, but in the new things that emerged from their collective dance. Suddenly, this whole puzzle of the FQHE had a natural, even elegant explanation, if you use the language of anyons.
So here's how the theory works. It says that the little ripples of energy, the excitations, in this 2D sea of electrons aren't just more electrons. They're totally new, emergent quasi-particles. And these quasi-particles, they are not fermions. They actually carry a fraction of an electron's charge. And, this is the kicker, they follow anionic statistics. Their existence perfectly, beautifully explains those strange fractional measurements that everyone was seeing in the lab. So you see, what started out as just a theoretical loophole, a weird little quirk of math in 2 dimensions, turned out to be the master key to unlocking one of the most complicated puzzles in modern physics. It basically opened up an entirely new frontier. And that journey from a wild idea to a confirmed reality was just incredible. The possibility of anyons was first kicked around in 1977. Then, just 5 years later, an experiment accidentally created the perfect mystery for them to solve. The fractional quantum Hall effect was discovered. It took a few more years, but by the late 80s, the connection was made, and anyons went from being this obscure little idea to a massive field of research. When you step back, the story of anyons is really a powerful reminder that our picture of the universe is completely shaped by the way we choose to look at it. They prove that just by changing your perspective, in this case by literally just removing one dimension, you can discover entirely new rules and even new forms of existence we never dreamed of. And that leaves us with one final, tantalizing question. If an entire secret kingdom of particles was hiding just one dimension away from us this whole time, what other incredible physics, what other fundamental secrets of the universe are we still missing just because we haven't found the right place to look yet?